welcome to PLU video 1. This is Mr. Mohan and let's start. Okay, so the 5 learning outcomes that is parked under the electrochemistry would be what you see in this first slide. Knowing what an electrochemical cell is, which is, again, it's something that's been covered at a basic level. It's covered in your high school, and we did a bit of that in Sem 1 when we compared electrochemical cell to an electrolytic cell. You are expected to be able to construct an electrochemical cell using the given information, such as half equation, electrodes, electrolyte, and something new called shorthand notation. Then, of course, the new addition to this component would be the ability to perform EMF calculation, electromotive force calculation, and of course then we will use that value to be able to predict whether redox will take place or not. And the last part would be the ability to perform free energy change calculation for the electrochemical cell that's given to you. Now this I will be delivering this 5 learning outcomes in 2 videos, and this is video 1 that will basically cover learning outcome number 1 to number 3. Okay, moving on. What is electrochemistry? Very simple. Electrochemistry would be the study of electron transfer and how this electron transfer in a very specific setup would lead to formation of electric current that can be measured. Now, how is this essentially achieved? It's achieved by placing electrodes in an electrolyte. There is a little bit of trick here. The electrolyte has to match the electron. We'll look at that more later. In a chemical reaction, now there has to be some rules that we have to adhere to ensure there is transfer of electrons that will take place, and that transfer of electrons in the external circuit would be recorded as a current. We can measure the current using the voltmeter. Now, a voltaic cell, an electrolytic cell. Okay, we have covered electrolytic cell in the semester 1. An electrolytic cell is the exact opposite of voltaic cell. An electrolytic cell runs on the principle of chemical reaction that is caused by electric current, which means there has to be a source of electric current, and in summary we can say electrical current change to chemical reaction. A voltaic cell is the exact opposite. We use the chemical reaction to generate the electricity. There will be no parts of electrolytic cell that's covered in this video or in this semester, as we have completed that in semester 1. Okay, now it's a bit strange to talk about standard hydrogen electrode. There's a reason for that, because we will look at a full setup in a bit, and you have to understand from where all the readings that is already given to you in your data booklet. I'll show you that as well in the upcoming slide. How did we obtain reading for each element that is listed in the standard reduction table? Now, this is a hydrogen electrode. You have to remember this. Of course, you're allowed to draw something that is much more simpler than this in the exam, but what are the important parts that must be found in a hydrogen electrode is the platinum wire, because hydrogen in its standard state is gas. So remember, this is standard hydrogen electrode. That means it's conducted at standard conditions, and in standard conditions hydrogen exists as a gas. So then how do we create an electrode that is generally metal, but here we have to use hydrogen? There's a reason why we use hydrogen. It has a relative potential value of 0. Now we will talk more about that in a bit. Hydrogen gas will be pumped in through here, and that will be maintained at 1 atmosphere, because again this is standard condition. And then there is platinum electrode that is connected. So the gas, the role of platinum wire here is to receive the gas and conduct it into the electrolyte. Now the electrolyte here is pretty important, that the electrolyte must be some sort of acid. So because generally we use strong acid, can be hydrochloric acid, it could be generally a sulfuric acid, and we use 1 mole because again 1 mole per liter is a standard cell. Now hydrogen, obviously hydrogen gas, that would be an electrode H2, and the electrolyte must be rich with the hydrogen ions. Okay, so that's a match, and the electrolyte must match the electrode. In the electrolyte you must have the ions of the electrode that we use. Now, why are we talking about standard hydrogen electrode? Simple reason, this is how reading or the reduction potential of each metal has been determined. we will pair the metals. As you can see, we pair the metal to, let me just get the pen. Okay, so the metal will be usually placed at one side, and the metal, again, if you have a metal electrode, and you will need to have the electrolyte that will have the ion of the metal electrode. So if this is magnesium, I will have to create an electrolyte that has magnesium ions. Essentially, that would be the electrolyte, and this will be matched on the other side with the half cell of a hydrogen electrode setup. Again, simple. If you could see, this drawing is a lot more simpler than the drawing that we saw earlier. Again, hydrogen gas, yeah, it says hydrogen, but you have to understand it's H2. It's always H2. At 1 bar, which is also more atmosphere, it's pumped in, and the platinum wire will be conducting it into the electrolyte. And again, if you could see, this example uses a sulfuric acid. Like I said, it doesn't matter what type of acid we use as long as it's a strong acid. Remember, 3 examples of strong acid, that would be sulfuric acid, nitric acid, and hydrochloric acid. Again, 1 mole per dm cube, because we need to conduct this at a standard condition. Only then the reading taken by the voltmeter will be a standard reading. Now, since the hydrogen half cell will represent a value of 0, the reading that the voltmeter would show us would be the reading that is for magnesium. Now, this is, you're not expected to be able to explain how we have arrived at the EMF, but this is normally delivered so that you can make sense of the standard reduction potential table. That's a table that's given to you, which I'll show you in a bit. Table is available in your data booklet. Now, other things about the general basic electrochemical cell that I want to add up is the presence of salt bridge. Now, this is important. This is quite basic, but I would like to explain this again. Why do we have a salt bridge? Why is it important to have a salt bridge in an electrochemical setup? Now, you could see that is what basically happened. I would like to summarize what happens using this acronym that I love, OILRIG. So essentially what it stands for is oxidation is loss, and reduction is gain. Okay, so what that simply mean here is referring to electron. So oxidation is loss of electron, reduction is a gain of electron, which means there is one cell here in this setup that is going to lose electron, and another cell is going to gain electron, and that's reduction. So what's happening is the individual species in each half cell will be either receiving electron or losing electron. So let's say in the event that it is losing electron on one side, which means it leads to formation of more positive ion, and on the other side you will end up losing the positive ion. So one cell will become more positive, another cell will become more negative, which is really not good if it's not allowed to be neutralized in a way that it will prevent the electron transfer. I would explain more on this using a better example that we have in the upcoming slide. But the role of salt bridge in simple term, why do I maintain a salt bridge, is to maintain electrical neutrality. Okay, maintain electrical, sorry about the handwriting, it's a little bit difficult to write on PowerPoint. Electrical neutrality. Okay, so how does it maintain the electrical neutrality? It allows the exchange of ions that are in the opposite charges. Okay, we'll revisit this in a bit. So you can see that how this is the half equations that we'll see for this cell. Okay, so simple idea, we measure the potential difference using 2 metals, and this is directly measured using a voltmeter. So the voltmeter would show the magnesium being the negative electrode, because usually there's very few electrons available around the hydrogen electrode. So the high amount of electrons on this side would end up traveling to the other side. That is relatively more positive. This is relative, so please take note of that. The reading of standard potential is in relative comparison to the hydrogen. So again, if you go back to the table that's given to you guys, which I'm going to show you in a bit, this is an example of the table. So if you look at the table here, we'll see that the hydrogen will have a value of 0, and everything else is measured against the hydrogen. And also take note that every single equation in this table is a reduction equation. Therefore, you can see that the name of the table is a standard reduction table or standard reduction potential table. So all of this are potential reduction, and the value here that you see is the standard potential for it. Okay, moving a little bit backward. Now, what is EMF? EMF stands for the electromotive force, and it's essentially the electric potential difference between two electrodes when there is no current drawn. Okay, now moving on, an example of a cell. Again, let's analyze what's happening in this cell. Copper is matched against zinc. Now, traditionally in your high school, you were expected to remember which is a more reactive metal, and by that you will remember that who will donate electron to who. So the idea is if you're more electropositive, then you have a tendency to lose electron to form positive ion. So in this case, you could see that how zinc is losing electron to its copper. Now, at this stage, we have the presence of the reduction table with us. We could easily use that to determine who will lose electron and who will gain electron, which is what we're going to do later. So at this stage, I just want to cover the basics of an electrochemical cell. Now, what is an electrochemical cell? It's made up of two cells that is connected by a salt bridge. And what is the role of the salt bridge? Salt bridge allows the transfer of ions that helps maintain the neutrality of each cell. Now you can see here the cell that is on the right hand side is a zinc half cell, which means you have a zinc electrode and you have a solution, an electrolyte that contains zinc. So it can be anything. It can be, for example, it can be zinc sulfate, or it can also be zinc nitrate. I love nitrates because you know nitrates does not form insoluble precipitates. So in that way, it's kind of safe to use nitrates in all examples. So that's zinc nitrate. There's zinc in this solution, and then there's obviously zinc electrode connected to the other side. You can see this is copper electrode in an electrolyte of copper solution. Now, when this is connected to each other, what happens is electron is released by the zinc electrode. Now, why? Simple. Zinc is undergoing oxidation. Now, this is important. I'm going to do the oil rig again. So, oil oxidation is loss, and you could use this to remember reduction is gain. So, A, C alphabetically. Oxidation. We'll write oil rig. All right, and oil rig. Sorry, oil rig. Reduction is gain. AC stands for anode and cathode. So anode and cathode. Now I always use this to decide which is which. Now in this case, you can clearly see that the electron is being released by zinc. So zinc becomes the source of your electron. So oxidation is taking place here, and the cell that always experiences oxidation is the anode. In this case, being the source of electron, you will be carrying a symbol of negative here. Okay, so electron travels through this external circuit all the way to the other half cell. So obviously here what's happening to the copper is undergoing reduction. It gains electron to become copper solid. Here zinc is obviously undergoing oxidation to form zinc ion. So what essentially happens to the zinc here, it will corrode and it will become thinner, and this side obviously copper will become thicker. Okay, now what's happening other than that here is that this solution is, since obviously the electrode is losing electrons, more and more zinc ion will be released into the solution. That kind of makes the solution to become more positive than before, which is not really good because you have electrons going out of this cell becoming more and more positive may actually attract the electrons back. Not only that, on this side you could see that more and more copper ions from the solution is going to receive electron on it and becoming copper solid. That means in this half cell you have loss of positive ions. That means this half cell is going to become more and more negative, right? Because nothing is happening to the sulfate ions. Before this, for each sulfate ion in the solution, one copper ion were there, kind of maintains the neutrality, positive cancel with the negative. But now since we are removing the copper ions, it's going to become more and more negative, which is not so good because you have electron that is negatively charged traveling towards this electron. That's why we use a salt bridge. Now, what does the salt bridge do? The positive ion from the salt bridge, like this, would end up moving into this half cell because this half cell is becoming more negative. So the migration of the positive ion into this half cell will kind of reduce the negativity of this half cell. On this cell just now, it was becoming more and more positive because of the formation of this zinc positive ion. You will have negative ion or anion moving into this half cell, therefore maintaining the electrical neutrality. So the half cell tend to last a little bit longer, actually not a little bit, it's usually a lot longer than electrochemical cell that is constructed without a salt bridge. Okay, so those are basics, and you can see the half cells can be used to construct the overall reaction. And if you're wondering what is this value over here, this is the standard electrode potential reading, which is provided to you in your data booklet. Okay, that's basics. Moving on, cell convention. Now this is important because cell convention, also known as the shorthand notation, is crucial. It's something new, it's high level, and normally we expect a student to be able to produce a cell convention, or if given a cell convention, should be able to produce the completely constructed cell. Now if you could see here, we will have, okay, this is a cell convention. I'll put all the points first so that I could use a pen, otherwise I'll lose the pen. Okay, so this is the cell convention. Now get used to this. This is cell convention. If you're wondering what is this is cell convention. It's a standard way of expressing this. This is really, really important. Now, what is cell convention? It's simply the easiest way of representing an electrochemical cell. Some of the rules: the anode is always written on the left. Remember anode? If you always forget what is anode, oil rig, I'm going to write for you again. So AC. Oxidation is loss, is obviously anode. It's the source of electrons, so it's negatively charged. Reduction is gain, and that's cathode. E is positively charged. I mean, it's a positive terminal. Here will be negative terminal. Now, anode is always written on the left. Cathode is always written on the right. And as you could see, this is the electrode. So you can see that there is a solid symbol there. That means it's the electrode, and then we'll use a single line to separate it from the electrolyte. We do not have to show the anion. I mean, when you construct, you may have used zinc nitrate, but it's okay, as those are spectator ions. We do not need to show them. So here's zinc 2+ aqueous. This is a must. The state is a must. This is the electrolyte, and the two cells are separated by this double line, and this double line represents the salt bridge that transfers the ions between the two cells to maintain the neutrality, followed by the electrolyte of the cathode, followed by the electrode of the cathode. So this is a must. Terminals are placed at the extremes. Terminals will be your electrodes. Single vertical lines represent the phase boundary, which is usually solid and aqueous, in exception to the standard hydrogen electrode. Okay, all right, so this is our convention. So I'm going to use this as an example. We're going to try to I'm going to construct one for you. I know it's a bit funny because I'm showing you the exact same example as before, but what will I do if this is given to me? Now, as I've mentioned, in case you forget, we revisit, anode is on the left, cathode is always going to be on the right. Okay, now that's not how you draw it. When you draw it, it's up to you where in your drawing or in your construction of an electrochemical cell, it doesn't really matter whether the anode terminal is on the left or right. But from this expression, we will derive the idea of who is undergoing oxidation and who is undergoing the reduction. Remember, anode is left and cathode is right. So if I were to give you another abbreviation of it again, so let's do that. So this is, okay, so just as reference, we'll put this down, oil rig, and simply oil rig is always going to be A, and here is going to be C. And remember, anode is always going to be the left. It's the one that is on the left, and here is the one that is on the right. Okay, that's That's the convention. So when I look at this, let's assume I don't know who's undergoing oxidation, who's undergoing reduction. I'm just going to focus on what's on the left. So obviously this is on the left and this is on the right. So if this is on my left, then this has to be the anode, which means this is going to be the oxidation cell and this is going to be the reduction cell. All right. So this is how you know what's happening. How does the electron move, whether it's from which terminal to which terminal. Now, when we draw it, it really doesn't matter if whether you're going to have copper on your left side or zinc on the left side. Remember, in terms of the drawing, it doesn't matter. But when we write the convention, we do have to keep the anode at the left and the cathode at the right. So I'm going to now draw. It's a very simple drawing. I'll try to keep it as neat as possible. I do apologize earlier if the drawing is not so clear. Now, okay, so I've done, this is my obviously beaker. Those are going to be my electrodes. Again, I'm just going to draw the electrode on both sides, and this is going to be my electrolyte, and that's my salt bridge. Okay, and don't forget to connect the external circuit to the electrodes, and obviously this is my voltmeter. Now we have to label. So obviously it's up to me, it doesn't really matter which is which, but just for sake of clarity, this can be my zinc electrode, then this has to be my electrolyte. So I can just leave it as zinc 2+. You know, generally we use 1 mole per dm cube. Zinc 2+. How do I make zinc 2+? It can be using zinc nitrate, it can be zinc sulfate, that's up to you. But like I said, the spectator ions are not really important to show. Now this will be copper electrode, Cu, and this will be the copper ions. So copper ions aqueous. Oops, really bad handwriting. That's because the PowerPoint is not so versatile in terms of writing. Now this is done. So what else do I need to add into my drawing? Of course, the movement of electron. Remember, zinc being at the left, left means anode, anode means oxidation. So electrons will be leaving zinc here, and that will be moving through the external circuit into this part. So that's electrons, those are electrons moving in. So having lots of electrons on it, that means here there's going to be reduction. So if reduction, what's happening in this half cell is copper ions are going to be receiving the electrons to form copper. Okay, for some reason the drawing is becoming worse. So here the zinc electrode, it's going to lose electrons to form zinc ions. Right, so that's going to be loss of 2 electrons. So remember, this is solid to aqueous, and that's the opposite there. From aqueous it's becoming, oh sorry, got this one wrong, so I'll just change that. It changes to copper, solid. So that's a bracket of S. Oh dear. Okay, so copper becomes solid by receiving 2 electrons. I'm sorry if this doesn't look like an electron. It's supposed to look like an electron. Okay, what's happening here is you are losing positive ion on this cell. The copper half cell is losing the positive ion. As a result, it tends to become more and more negative because the N ion is left here. So what will happen is the positive ion from your salt bridge would actually move into this half cell. And this side, you have more and more positive ion being generated from the oxidation process. Obviously, the cell becomes more and more positive. So negative ion from this half cell would move into this. Okay, so this is generally how we construct an electrochemical cell using a cell convention. Just to show you another example. So now what will happen is you're expected to write the shorthand notation to describe the cell that is formed using copper and silver. So now this is the question: between copper and silver, who is going to be the oxidant? So again, oil, rig, and this is obviously anode, cathode. This is going to be on the left, this is going to be on the right. So now at this stage here, you may be a little bit troubled because you're not sure who's going to lose electron. Whether is copper going to lose electron to silver, silver is going to lose electron to copper. For those people who still remember your electropositivity series, you may find it a little bit easier. For those who don't, no worries, we can always use the electrode potential table. So I'm going to go back and show you the electropotential table. This is electropotential table. What we can derive from this is, you can see all the equations are showing the reversible line, and you can see the value. The value being negative means to say that this is less likely to go as written, or a negative value means it's more likely to be reversed, which means the higher you go, you're more likely to be reversed. Meaning, let's look at, that was a cell of copper. There you go, this is copper, and where's silver? Silver is here. So silver located much lower. Silver has a more positive value, which means silver's value is 0.8. It's a lot more positive than the copper's value. Copper's value is 0.34. So being more positive, having a much more positive or much more larger reduction value indicates that the silver ion is more likely to be reduced, which means copper is more likely to lose electron to silver. If you remember, this would be matching to the electrochemical series or electropositivity series that you have studied in your high school. So copper here will lose electron, the copper will lose electron to silver. Moving back to cell convention, let's try, just now I've drawn, now I'm going to try to write it down for you. So again, we'll put down our formula. Remember, this is just to help you oil rig, anode, cathode, left, right. Okay, so copper and silver. So we know that copper is going to be the oxidant. It's obviously the anode. So in this case, copper is going to be the anode and silver is going to be my cathode, which means on the right. So very easy. We're going to start with copper, always at the terminals. Copper, solid, separated by a single line. Then copper ion, which is the electrode. This is aqueous, double line to separate the cells and to show the presence of a salt bridge. And then again electrolyte, so silver Ag plus, separate by a single line to give the electrode. Electrode would be at the terminal, so I have to put aqueous here, that's a must, don't forget. And here is solid. There you go. This is how you write a shorthand notation. Now I think it's pretty simple. I'll repeat back. You just have to remember that the terminals has to be the electrodes. So you can see the copper solid is here and the silver is here. They're separated by a single line to their electrolytes. Now what's on the left? The cell that undergoes oxidation is going to be on the left, and the cell that undergoes reduction is going to be on the right. So how do you decide this? You decide this by looking at the standard reduction potential table. You can see the one that's further high up will always lose electron to the one that's lower. It's almost like remembering it as somebody who's a higher status in life can always donate to somebody with a lower status in life. Okay, that may not be the best example, but it kind of helps you to remember. Or you can think of it as, you can see that all the equation given to you on the reduction potential table, they're all reversible equation. You can think of it as that, like this: the more positive the value, the more likely the equation is to go forward. The more negative is the value, the less likely for the reaction to go forward. Or you can think of it as more likely to be reversed. And you can see in which side is the electron, and you would know that which is undergoing oxidation and which is undergoing reduction. Okay, so one more. This would be the last part of the this video. That would be calculation of the standard electrode potential, and you can see in bracket here there's the word reduction. Now why? Because simple, we are using a table of reduction which is essentially measured against the hydrogen cell. EMF is the difference in value between the both cells that is paired against each other. The simple formula here that you could see is what's at the bottom here. The formula is pretty important. You can memorize it, or you can simply get used to it. I like the getting used to part. Oxidation potential and reduction potential. Okay, what it simply means, the table that's given to you is reduction potential table. But when you construct an electrochemical cell, one half of the cell will experience oxidation and the other half of the cell would experience reduction. As a result, we will have to decide who is who before we could plug it into this formula. You can see this E naught, that's simply symbol for standard conditions, half cell containing the oxidant and the half cell containing the reductant. Now I would like to remind you, oxidant also means oxidation agent, reductant means reducing agent. Oxidation agent would undergo reduction, whereas reducing agent would undergo oxidation. Now that's a very important concept, very basic, but try not to get confused with it. Now let's put this into action and see what it simply means. Okay, so back to this table. This is nothing, this is just telling you what it is. We have already been through this. Now this is the table. You can see the table that's given to us has values. This is probably one of the most important slide for this part. Please take note, you do have to understand what this table is. This table that is given to you in your data booklet is a reduction table. All the equations that's written here are all reversible. You can see they always use the reversible sign, and the hydrogen electrode will always carry a value of 0. And you could see that the top part is negative, and as you go down past 0, it becomes more and more positive. Now simply means if I'm negative 3.04, this reaction is more likely to be reversed. Okay, so let's compare that against maybe lead. Lead has a value of negative 0.13. If I'm pairing lead against lithium in a cell, lithium is more likely to be reversed, lead is more likely to be moving forward. I mean the forward reaction, because lead is relatively more positive than the lithium, which means lead is more likely to be, if I'm moving forward, what's happening to lead? Take a look at this equation. Lead is obviously undergoing reduction. So if this is the lithium is more likely to be reversed, that means lithium is likely to be undergoing oxidation, which means lithium will end up losing electron to lead. Okay, so that's what it simply means. Repeat that. Okay, so another way to remember this obviously is also by simply remembering that the best oxidizing agents are those at the bottom of the table and the best reducing agents on the top. Remember, if you're a reducing agent, that means you yourself will undergo oxidation, or if you're an oxidizing agent, you yourself will undergo reduction, which means, in another word, those species that is above will always lose electron to the below, which means those species above in this table will undergo oxidation and the species that's below will undergo reduction. Okay, so now that we have understood the table, if you don't, just you may want to rewind a little bit and listen to what I've just said again. So this is not generalization from the table, is simple as what I've just given to you. The oxidants are on the left hand side and the reductants on the right hand side. What they mean by that is simply this table. You can see that what's on the left is obviously gaining electrons, on the right is the one that tend to lose electron, depending on which way you look at the equation. All right, we're going to go through, skip that because that's not really important. This is now back to the formula. I want to go straight to working out something. I don't need all this. We don't need this. Again, where are the examples? Okay, all right, there you go. All right, so now they say that let's calculate the standard EMF of zinc copper cell. So when I say standard zinc copper cell, I need the table. So when I go to the table, this is what's there. Okay, you can ignore the solution, just follow my pen here. This is zinc and this is copper. So if you go back to the table, you will realize zinc will have a reduction potential of negative 0.76. Copper, on the other hand, have a reduction potential of positive 34. In another word, if you look at the table again, I would encourage you to have your data booklet with you right now. So you can flip, you can go and take a look that the zinc half equation is obviously in a much higher place compared to the copper, assuming you're looking at the reduction potential table, which means zinc will obviously undergo oxidation. It will lose electron to copper. right? So since you're looking at a reduction potential table, but what's happening in your cell is zinc is undergoing oxidation, we need to change the value to positive. Whereas copper's value will remain the same because it is undergoing reduction. And the value from the reduction potential table is 0.34. Now, if you have manually changed these values, this is what I call as a manual changing, then all I need to do is to calculate the EMF of cell. I just total the both values. 0.76 plus 0.34. The cell will have an overall EMF of 1.1 volt, positive 1.1 volt. Now, that's another way of doing this. You could see that this formula that I've used here is slightly different looking than the formula that you looked at earlier. All right, we just quickly go back to that slide. I think I might have that at the back here. Okay, so there you go. This is the other one. So you could see that that formula had an addition and this formula has a subtraction. But don't get confused, it's actually the same thing. It's just a different way of looking at it. This cell, if you're using this formula, we do not have to reverse any of the sign, but we do have to realize that this is oxidant minus reductant, which means the species that's undergoing reduction will minus the species undergoing oxidation. Okay, so don't get confused. I'm gonna post another video very quickly to show you some of the worked examples of EMF calculation. This is going to be the questions that I will solve for you, and a few others that you could watch, and then obviously you have to go to Checkpoint and give it a try. Okay, don't forget to make a consultation with me if you do not get this. The underlying issues usually the knowledge of basic electrochemistry. Okay, so please watch this again, slow down, revisit parts that I've mentioned, and then go and look at some of the worked examples for the EMF calculation. Okay, that's the end of video. Sorry, I'm going to say that again. That's the end of video 1, and I'm going to end up making video 2 very soon. Thank you very much. Bye-bye.